Good morning, student. I welcome you all once again to my YouTube channel. Today onwards, I'm going to discuss lectures on microprocessors and microcontrollers. For this class, I just give brief idea or an introduction about microprocessors. Topics to be covered: introduction to microprocessors, history of microprocessors, basic microprocessor architecture, Harvard and von Neumann architectures, CISC and RISC, microprocessor versus microcontroller. Coming to introduction to microprocessor, what a microprocessor is. We can define microprocessors in different ways. Here I'm going to give some of the definitions for microprocessor. The first definition is the CPU of any microcomputer is called microprocessor. Most of your microprocessor textbooks contains this definition for microprocessor. The CPU of any microcomputer is called microprocessor. That means what are the job a CPU can do in computers, the same job can be done by microprocessor. And what are the internal parts a CPU has, the same internal parts present in microprocessor. This is the first definition for microprocessor. Coming to the second definition is a small device which is able to do data processing is called a microprocessor. That means here I simply split microprocessor word into two halves like a micro and a processor. Micro means a small device. Processor means a device which can process the data. I combine these two and I give a second definition for microprocessor, that is a small device which is able to do data processing. Coming to the third definition, microprocessor is a microprogrammable device that takes binary data from an input device, instructions from memory. It can process the data as per the instruction and produce the result. It was sent to the memory or to an output device. Basically, this definition speaks about what a functionality of microprocessor is. In a first definition, we already quoted that microprocessor is a CPU. So that what a CPU can do? The CPU can execute programs. Similarly, here what a processor can do is it take a binary data from an input device and it took instructions from the memory. It can process the data according to the instruction and it produces a result and it is sent back to the memory or to an output device. Coming to another definition for microprocessor is microprocessor is a semiconductor device. It consists of ALU, CU and a group of registers. It is also related to the first definition because in a first definition we mentioned about microprocessor is a CPU of a microcomputer. What a CPU contains? It contains ALU, arithmetic and logical unit. It contains control unit CU. Along with this, it contains a group of registers, or simply we can call a set of registers. By considering of that, I give a fourth definition for microprocessor. Microprocessor is a semiconductor device. It consists of ALU, a CU, and a group of registers or register set. I hope you understand what a processor is. The first definition, that is CPU of any microcomputer, is called microprocessor. I think, or my feeling is, this definition I was quoted based on the application where exactly processor was used, most of the cases. The second definition based on the name of the device, I define a microprocessor like this. And third definition based on its functionality, what a microprocessor can do for us. And a fourth definition, I give what internal components contents in a processor. Like this, we can define a microprocessor in different ways. Next, history of microprocessors. This concept we can also call the classification of microprocessor based on word length, or we can also call generations of microprocessors. First of all, what is meant by word length? Word length means the maximum number of bits processed or recognized by the CPU at a time. Or I can say in another way, how many number of bits a processor can handle at a time. That means on how many number of bits a processor can perform either arithmetic operation, logical operation at a time, and how many number of bits at a time it can transfer to memory or an IO devices, or how many number of bits it can receive from memory or an IO devices maximum at a time. That indicates word length. Indirectly here, this processor is related to the capacity of ALU, means basically arithmetic and logical operations are performed by ALU. Here the data processing function was done by ALU in central processing unit. So that here this processor word is related to ALU capacity. Number two is recognize. This is related to how many number of data lines a processor has. With the help of those data lines only, your processor either transfer a data to memory or an IO devices and vice versa. So based on this word length, we can classify the processors into different groups. We can also call the generations of processors. So as of now, I divide a processors into 5 generations. First generation processor, second generation processor, third generation processors, fourth generation processors, and fifth generation processors. Now I'm going to discuss these generations one by one. Let's come to the first one, first generation microprocessor. For the first generation microprocessor, the word length is 4 bits. That means these processors can do their task maximum on 4 bits at a time. The example processors are 4004 and 4040. The first microprocessor in the world was basically 4004. It was designed by Intel Corporation. The design technology what they are using for making of this first generation processor was PMOS technology, means P-channel metal oxide semiconductor technology was used for making of first generation processors. I already quoted that the first processor in the world was 4004. It was designed by Intel Corporation in the year 1971. The basic aim of designing of this 4004 was, it was used in calculators. The calculator's name is BuzzyCom. Basically, 4004 processors are designed to be used in BuzzyCom calculators. Later, we are using processors as a CPUs in our computers. The advanced version of 4-bit microprocessor is 4004. It was introduced in 1974 by Intel. The basic difference between 4004 and 4040 is, number one difference is how much program memory it can support and number of transistors it has. The program memory supported by 4004 is 4 kilobytes and number of transistors it contains is 2300 transistors. Coming to 4040, the program memory supported by 4040 is 8 kilobytes and number of transistors it has is 3000 transistors. Anyway, we can say that 4040 is advanced version to the processor 4004. This is about the first generation microprocessors. Coming to second generation microprocessors, the word length is 8 bits. That means compared to the first generation, the word length was doubled. That means second generation process can do the operations maximum on 8 bits. That means the speed of operation of second generation processor automatically doubles than first generation processors. The examples of second generation processor 8008, 8080, 8085. These are three processors from Intel. And another one is M6800. This is a processor from Motorola. And Z80 from Zilog. Coming to the second generation, so many manufacturers comes onto the picture in the designing of microprocessors. That we understand from these examples. The design technology, what they are using for making of second generation was NMOS technology. NMOS means N-channel metal oxide semiconductor technology. Here an interesting thing was the processor 8080, which comes from an Intel. For its operation, it requires three power supplies. Those are plus 12 volts, minus 12 volts, and plus 5 volts. This is, I think, so only the one processor which requires three power supplies for its operation. But most of the processors just need only a single power supply. That is, I'm not talking about number of VCC pins, how much power supply we should go and apply to the processor operation. In the second generation process, 8085 was famous microprocessor. Almost it is, we can call the first general purpose, user-friendly 8-bit microprocessor. It was introduced in March 1976 by Intel. The speed and complexity of these processors is high compared to the first generation. Already we know that it has an 8-bit processor, so that automatically the complexity of your processor is increases. It can do more tasks. And the speed of operation of these processors also increased because the word length was doubled compared to fourth generation processors. Next, coming to third generation microprocessors, the word length was doubled compared to second generation, that was 16-bit here. Example processors for this third generation are 8086, 8088, 80186, 80286. These all from Intel. 680, 000, that is from Motorola. Z8000 from Zilog. Coming to the design technology of third generation processors was HMAS technology. What HMAS means? High speed or high density mass technology, but it is not hybrid mass technology. Just you remember, friends. HMAS means not a hybrid mass technology. HMAS means high speed or high density mass technology. The first 16-bit processor is 8086, and it was introduced in the year 1978 by Intel. Here, a special processor was that was 8088. Its internal architecture looks like a 16-bit, but it has 8 data lines, that is 8-bit data bus and 20-bit address bus. From this, what we understand is your 8088 operation looks like 8086 because 8086 have a 16-bit internal architecture, so that your 8088 operation looks like 8086 for the internal operations. But for external operation, the operations looks like 8085 because 8085 is an 8-bit processor and it has 8 data lines. And last one is the speed and complexity is high when compared to previous generations. That is 8-bit processors or 4-bit processors. That means second generation and first generation processors. You compare those generation processors with this third generation. The third generation processors have high speed as well as complexity also high. Next, coming to fourth generation processors. The fourth generation processor word length is 32-bit. Again, the word length was doubled, so automatically the speed of operation and complexity of the processor increases compared to previous generations. The example processors are 80386, 80486, some are Pentium processors. These are all from Intel, and M68020, M68030, etc. These are from Motorola. The design technology for fourth generation processor was HCMOS, means high speed or high density CMOS technology. One interesting thing is to improve the speed of operation of systems. We'll go and use some of the concepts like virtual memory concept, cache memory concept, and instruction pipelining concept. These concepts are introduced in this generation processors. The first one is virtual memory concept was introduced in 80386. Cache memory concept as well as instruction pipelining concept both was introduced in 80486. The 80486 processor supports a 4-stage pipeline, and automatically the speed and complexity of these processors is high compared to previous generations. Then coming to the last, the 5th generation processors. Their old length was 64-bit. Some of examples for 5th generation processors are Itanium, Pentium processor 4F, Pentium D, Xeon. Right now we are using i3 processor, i5, i7. All these are comes under this 5th generation microprocessors. These examples are from Intel. The design technology is same as a 4th generation HCMOS. We know that HCMOS means high speed or high density CMOS technology. Efficient memory management concept was introduced in this generation of processors, along with pipelining concepts, along with cache memory concepts, along with virtual memory concepts, and dual core, quad core concepts. All these are introduced in this 5th generation processors. Finally, we know that the speed and complexity of 5th generation processors are high when compared to previous 4th generation processors. I hope you understand what the generations of processors. Then coming to the basic architecture of microprocessor. We know that microprocessor is like a CPU. So that here I consider a microcomputer architecture or a block diagram. The microcomputer consists an input device, output device, memory elements along with a processor, because we know that the CPU of any microcomputer we call as microprocessor. What a microprocessor contains? Already in the definition part, in a 4th definition, I mentioned that microprocessor consists arithmetic logical unit, it consists control unit, it consists a register array or a group of registers, or simply we can call a register set. What this particular block can do, the name itself indicates arithmetic and logic unit. It can do different arithmetic operations like addition, subtraction, multiplication, division, increment, decrement. It can do different logical operations like logical AND, logical OR, logical XOR, complement, negation, rotation, shiftings. All these operations are done by your ALU. The second one is the control unit. Originally, this is act as a heart for your processor, because this is a unit which can generate the required control signals which are necessary for proper operation of your processor. As well as not only this is the part which can generate a required control signals for processor operation, it can also generate a control signals for an input output devices along with memory elements. And last part is a register array or a group of registers. This is the part which is helpful for us to hold the information temporarily before being attached by arithmetic and logical unit. As well as after completion of operation by ALU, this part is useful for us to hold the result temporarily. Based on a processor, the capacity of ALU may changes. The number of operations supported by ALU also changes. And based on the processor, the number of registers and their sizes are changes. So that the CPU of any microcomputer is called microprocessor. So what a processor contains, these are the major blocks. Then, so Harvard and Van Neumann architectures. So why I'm discussing about this one is, in a history of processors, we learn about what are the different processors we have. The same concept I already told to you. It is considered as processor classification based on word length. Similarly, we can also classify the processors by considering architectures. We design our systems by using these two different architectures. One is a Harvard architecture and second one is von Neumann architecture. We can also classify the processors by using architecture. That is, one variety of processors we can call Harvard architecture based processors, and second variety of processors we can call von Neumann architecture based processors. Now we go and see the comparison between these two. The first one is in von Neumann architecture, there will be a common memory which can store both programs and data. This von Neumann architecture we can also call stored program concept based architecture or Princeton architecture, because the von Neumann proposed a stored program concept. Nowadays, what are the systems we are using in that? We are using that proposed concept, stored program concept by von Neumann. Von Neumann proposed this concept in the University of Princeton. So that's why these architecture have alternate names like Princeton architecture as well as stored program concept based architecture. What this architecture contains? This architecture consists a common memory should be there in a system which can store both the programs and data. But coming to Harvard architecture, it says that we are not using a common memory to store both the data and the programs. We'll go with the separate memories, one for programs and another one for data. Then coming to the second one, once we have a common memory, single bus is used to access both the data and instructions from the memory because we have a common memory. But coming to Harvard architecture, we should use two separate buses are used to access information from data memory and program memory because we have two separate memories. Coming to the third one, it takes two clock cycles to execute a single instruction. Here my intention is, in one clock cycle, I'll go and access a data. In another clock cycle, I'll go and access an instruction. Once I access both the data and instruction, then I'll start execution. Because here I was using only common memory. That memory can hold both the data and instructions. Don't think, friends, here in two cycles it can go and execute a program. That is not my meaning. Here my intention is, in a single clock cycle, I'll go and access the data from the memory by using that single bus. In second clock cycle, I'll go and access instruction from the memory. But coming to the Harvard case, it is completely reverse. In a single clock cycle itself, I'll go and access both instructions and data from two separate memories by using two separate buses. So I can execute an instruction in single clock cycle. That it means. Then coming to the fourth one, von Neumann architecture takes more time for execution of instruction, obviously, because it takes two clock cycles that I was mentioned in a previous point to access the data, and the instruction was not done simultaneously because we have only single bus and we have a common memory. But coming to Harvard's architecture, it takes a less time for execution of instructions because in a single clock cycle itself, we can access both the data and the memories by using two separate buses from two separate memories. So execution time is less in case of Harvard architectures, but execution time is more in case of von Neumann architectures. Then coming to the complexity point of view, your von Neumann architectures are less complex so that the architecture is simple, but Harvard architecture is complex. The reason is here two separate buses we are using to access the information from two separate memories. Obviously, the complexity of Harvard architecture is more. I hope you understand the comparison between Harvard architecture and von Neumann architecture. Next, coming to RISC and CISC. This is another classification of processors based on the instruction set. We classify them into two types. One type of processors we can call CISC processors, and another type of processors we can call RISC processors. I'm already told you in the first, that is the processors we can classify based on word length. Previously, I can told that processors are classified based on architecture. The third one is here, I was classify them processors into two different varieties based on consideration of the instruction set, that is a CISC and RISC. Coming to the comparison between this, the first point, the expansion of CISC is complex instruction set computer, and the RISC expansion is reduced instruction set computer. What does it mean that I was mentioned in the next? An instruction set contains more number of instructions. That is the meaning of complex instructions. The complex instructions in the sense, the number of instructions present in the instruction set is more. It is not a meaning of it has a complex instruction, it doesn't have a simple instructions. That is not a meaning. Complex instructions means it contains more number of instructions. Coming to RISC, reduced instruction set computer, that means it contains less number of instructions. That is the meaning. Why it has a more number of instructions? Here I was mentioning a point, that is it supports more number of addressing modes. Once it supports a more number of addressing modes, we can go and represent an instruction in a different possible ways. But coming to RISC, it supports a less number of addressing modes. And one more reason why we have more number of instructions in the case of a CISC is to do each and every operation. That operation may be a simple or a complex. We have a dedicated instruction we identified in CISC instruction set. But coming to reduced instruction set, that is not a case. What are the operations we are not performing on regular basis? For those operation related instructions are removed from the instruction set. That's why the number of instructions present in the RISC was less. And next one is, if you go for a CISC, you may identify that variable instructions. That means variable length instructions you may identify. Some of the instruction size is 1 byte, some of the instruction size may be 2 byte, 3 byte, 4 byte, 5 byte, 6 byte, like this. But coming to the RISC, you may identify that fixed length instruction. That means if a RISC processor and instruction contains in its instruction set is some 4 bytes, if you want to refer any instruction, every instruction size is 4 byte itself. We never identified different length instructions in case of RISC. Then coming to the advantage of CISC is, the programs are developed with a less number of instructions, because to do each and every operation, we have a dedicated instruction in its instruction set. At the same time, the disadvantage of RISC is, the programs are developed with a more number of instructions. The reason is, in case of RISC instruction set, we never identify instructions for each and every operation. But what are the operations we didn't have an instructions? Those operations we perform with a combination of instructions. Let it be, you can assume the case like this. For example, I want to need a multiplication instruction. I'll identify directly that multiplication related instruction in case of CISC instruction set. But coming to the RISC, that multiplication operation I was not done regularly, so that I was removed the multiplication related instruction. Whenever if I want to do that multiplication operation, I'll do it by the combination of addition and shifting. I need a 2 instruction there. Because of this type of reasons, the programs are developed with a more number of instructions in case of RISC. And another one is, in case of a CISC, the control unit what we are using is microprogrammed control unit. But coming to the RISC, it contains hardwired control unit. Once a RISC have a hardwired control unit, it can generate a control signals at a faster rate, so that the speed of operation of your RISC system is more. That I was mentioned in the last but one point, the speed of operation is high. Once your control unit is microprogrammed control unit, it can generate a control signals at a slower rate, so that the speed of operation of CISC is low. That I was mentioned at the end. And coming to the next point is, we can easily to add a new instruction to existing instructions in case of CISC, because it contains microprogrammed control unit. Once a control unit is microprogrammed version, it is easy to add a new instructions to the instruction set, because we just go and develop some microprograms. Those microprograms we stored in a control unit, the control memory. It is done easy way, so that we can easily add a new instructions to the existing instruction set. That was possible in case of CISC. But coming to the RISC, it is very difficult to add new instructions, because in a hardwired control unit, the control signals are generated by dedicated hardware circuits. It is very difficult to add a new hardware circuits internal to hardwired control unit for generation of control signals for newly added instructions. So that difficult to add a new instructions to the existing instructions. That is the case for RISC. And one more thing coming to the CISC is pipelining is not effectively implemented in case of CISC systems. The reason for this is in case of CISC, we identify that a variable length instructions. Once the length of the instruction is varies, execution time of the instruction also varies. So that we were unable to implement a pipelining concept more effectively in case of a CISC. But coming to opposite in a RISC, pipelining concept is effectively designed or implemented in case of a RISC. The reason is in case of a RISC, you may identify that fixed length instructions. Once the length of the instruction is fixed, automatically execution time of instruction also fixed. So that the pipelining concept was effectively implemented in case of RISC system than CISC. I'm already quoted this. The next point, that is speed of operation is low in case of a CISC, and speed of operation of a RISC is high because the control signals are generated faster rate. And here I would like to add one more point, that is in case of a CISC architecture, you may identify that less number of registers. That is also another reason why the speed of operation is low. But coming to the RISC, you may identify that more number of registers. That is another reason why the speed of operation of a RISC is high. Once we have a more number of registers available on the CPU, automatically your CPU occasionally only it will go on communicating with the memory elements to access the data. But coming to the CISC, it is quite opposite. Once you have a less number of registers, regularly you should interacting with the memories to access the data, so that the time required to execution of program maybe increases. So that is a point you should remember. And coming to the last, the cost of CISC system is less because the speed is less, because cost and speed is directly proportional. But coming to a RISC case, the cost is more because the speed of operation is more. I hope you understand CISC versus a RISC. And last, coming to the last one is microprocessor versus microcontrollers. So here I would like to quote 7 points regarding to processors and controllers. The first one is basically a microprocessor is a single board CPU. We already know up to this. I quoted microprocessor CPU of a microcomputer. So that I was mentioned here, a single board CPU is called microprocessor. The single board in the sense, what are the components that should be present in a CPU? ALU, CU, and a register array or a group of registers should be present on a single board that we are calling as a microprocessor. Coming to microcontroller, a single board computer is called microcontroller. That means what are the components we identified in a computer like a CPU, memory, input, output ports? All these are present on a single board that we are calling as microcontroller. The second point, it is comes from first, what a microprocessor contains. Microprocessor contains ALU, GPRs, PC, SP, all these are the register array. Control and timing circuit, that is nothing but our CU, and interrupt circuits, etc. These are the additional features. Coming to microcontroller contains the microprocessor, nothing but a CPU. It contains inbuilt ROM, inbuilt RAM, IO ports, and timer and counter circuits. So this is a point we are getting from the first one. Your computer contains CPU. Your computer contains memory elements, both ROM and RAM. It contains IO ports for connection of external devices. All these are present on single board. In addition to that, it have an additional features, that is, it may contain timer and counter circuits. The next one is in microprocessor, it has many instructions to move data between memory and a CPU. In the instruction set of microprocessor, we may identify that more number of instructions are used to transfer the data between a memory and a CPU. But coming to microcontroller, it should be contrast, that is, its instruction set contains a less number of instructions or a few instructions to move data between memory and CPU. Because it has an inbuilt ROM and RAM, when it was interacting with the RAM locations, or it was interacting with an IO ports, you just treat them like a registers, so that we use the less number of instructions to communicating with the memory and IO devices with your CPU. Coming to the next point, more access time for memory and IO devices. The reason for microprocessor is your memory elements are not present on microprocessor. And next, the IO devices, that means IO ports also not present on microprocessor. So that we should interacting with this memory and IO ports external to your processor obviously takes much more time. But coming to the microcontroller case, we can say that less access time for inbuilt memory and IO device communication. Because it has inbuilt memory was there, it has inbuilt IO ports are there. Whenever your CPU was interacting with any inbuilt memory location or IO ports, it takes a less time. That is the meaning of this. Next one is microprocessor based system requires more hardware, obviously. Because if you are made a system by using microprocessor as a CPU, along with that, we need a memory elements, we need a IO ports, we should connect them. For that case, we need a more hardware. But coming to microcontroller case, microcontroller based system require less hardware. The reason for this is microcontroller inbuilt it has a memory elements, inbuilt it has an IO ports, so that most of the application we can use them. So less hardware is required for making a microcontroller based system. Coming to the seventh point, I'm not going to 6th point first, I'll go to 7th point. The 7th point indicates that less number of pins are multifunction in case of microprocessor. That means signals which are available in your processor, those pins have a dedicated functions. In this case, what we are doing is some of the signals have dual function. That means such type of signals count is less. Once your processor have a less number of multifunction signals, then automatically, once you have a less number of multifunction signals, the less number of operations we can perform. But coming to the microcontroller case, we may identify that more number of signals have multifunction. Once it have a more number of pins of multifunctions, it can do multiple tasks. By considering all these points, we price a microcontroller. Microcontroller is far better than microprocessor. But still we are using microprocessors in our systems. We are not replacing them with the microcontrollers. For that, the reason is the 6th point. Microprocessor based system is more flexible in design point of view. But coming to microcontroller based system, it is a less flexible in design point of view. The meaning of this one is while we are designing microprocessor based system, we select whatever the processor we need for our application, how much memory is needed and what type of memory is needed. We can select it, and whatever the IO ports are needed, we select it. By selection of all these things, we made a system. So here I have more flexibility. But coming to microcontroller case, the flexibility is less. The reason is your microcontroller have inbuilt memories, we have inbuilt IO ports. There is no much choice for you for selection of memory elements as well as IO ports. Most of the cases we go with the memory elements, IO ports, what are available on the microcontroller for making of a system. So that the design flexibility is less in case of microcontroller based systems than microprocessor based system. This is the reason why still today also we are designing a microprocessors and we are using them into different systems. I hope you understand what is the difference between a microprocessor and microcontroller. Thank you for patient listening. In the next class, we're going to discuss some other topic. Once again, thank you very much.